Now, one of the areas where pH and charge become very, very important in thinking about the structures of biological molecules. And remember, in biochemistry, we care a lot about molecular structure because you remember the old adage, form is function, function is form. So we really need to understand a lot about how biological molecules are formed and how they interact, right? And how those structures dictate those interactions. Now we're going to start looking at the covalent structure of molecules like proteins, carbohydrates, and lipids. But the biologically relevant conformations of those molecules are only partly specified by those covalent linkages, many of which you've studied in some detail before, hopefully. There's a variety of weak interactions that individually are not strong. No, they're an order of magnitude to 2 orders of magnitude weaker than those covalent bonding interactions that hold the basic structure of these molecules together. But they're present in huge numbers, and in such huge numbers that their individual properties have super important implications for how biological molecules behave the way that they do. And we need to understand something about these interactions in order to explain and understand how these basic aspects of biochemistry work. Okay, so these weak interactions, as I said, are weak by definition or reference to a covalent bond. And they also tend to be short range. And when I say short range, I mean typically less than about 10 angstroms in distance. You get outside that range for most of these interactions and are most biologically relevant conditions, they essentially don't exist anymore. They're not relevant any longer, right? And we're going to group these into a set of categories, and we're going to start with the strongest first, and then sort of move on to the weakest, and then I'll backtrack a little bit to another interaction that's kind of bridges the gap between these fully weak interactions and a covalent interaction, right? So let's just start out. So the first of these weak interactions we're going to talk about are so-called charge-charge interactions. And these are also sometimes referred to as salt bridges. And a good example of an interaction like this, a charge-charge interaction or a salt bridge, is of course something like the interaction between, say, a deprotonated carboxylate group and a protonated primary amine, for example, where we know this is positively charged. We have a negative charge here, right? And we know there's going to be an electrostatic interaction between those two groups. And let's just, for reference, now let's call this guy group A and this one group B, all right? Because turns out we can specify the energy in that electrostatic interaction between these two charged groups quite precisely. And the energy is quite significant. This was first worked out by Coulomb many years ago and captured in Coulomb's law, which looks something like this, where change in energy of that interaction is equal to K times Z sub A. I'll define these terms in a minute for you, Z sub B, divided by this term epsilon and RAB, right? And in this case, delta E is equal to the energy needed to move those two charges basically from a distance r, which is the same r that you see in the equation there, to infinity, right? So essentially, if you have those two distances at some given distance, and then the amount of energy necessary to move them from that distance to an infinite distance away from each other sort of defines the energy of the interaction, right? Z sub I, in this case, is the formal charge, on the ion. K, in this expression, is the unit charge on an electron. R sub AB, in this case, is the distance, as I said, between the two groups, right? And that epsilon value is something known as the dielectric constant. Okay, so in a vacuum, of course, you guys maybe remember this, that in a vacuum, the dielectric constant is 1, right? Which if you, again, look at Coulomb's law, if the dielectric constant is 1, it's going to make essentially no contribution to the strength of that interaction, right? Between the two groups, or they will be maximally energetically attracted to one another, given the rest of the parameters of Coulomb's law. However, we don't operate generally in vacuums. Usually biological organisms die in vacuums, right? So we're typically thinking about things like in water, and the dielectric constant of water is really quite high. It's around 78 to 80, right? So if you think about that same idea, instead of substituting in a 1 here, you substituted in something like a value of 80, you can see what's going to happen to the strength of the interaction between those two charged groups. It's going to go down by almost 2 orders of magnitude, right? Almost 100-fold weaker. So the charge-charge interaction, the salt bridges are really strong, really powerful, but putting them in water attenuates and weakens them significantly relative to what they would be in a vacuum. Now, that doesn't mean that they're no longer important, right? It just means their ability to provide a stabilizing interaction or an attractive free energy is reduced in water. But interestingly enough, and you'll see this in lots of cases in biology, if those charged interactions in two groups, two parts of a protein, whatever, are isolated from solvent, if they're basically screened away from intervening water, those interactions can bump right back up to the top of the scale and become extremely important. And they can, in some cases, be linchpin interactions that you disrupt them and the entire molecular structure will fall apart, right? Okay. So electrostatic interactions, charge-charge interactions, are super important, but there are other kinds of electrostatic interactions, a whole family of additional electrostatic interactions that are just as important and considerably weaker, right? So it turns out that there are plenty of molecules that don't have a permanent formal charge on them, right? Carry no regular formal charge, but they have an asymmetric distribution of charge that can lead to electrostatic interactions because of that asymmetric distribution of charge, right? Now, as a good example of this, consider this molecule. You have an oxygen, and then a hydrogen, and another hydrogen. You guys know that molecule, of course, that's water, right? But what do you know about the electronegativity of an oxygen atom, right, versus a hydrogen atom? Well, hopefully you remember that oxygen is considerably more electron withdrawing than hydrogen, which means that these oxygen-hydrogen bonds are not symmetric on the length of the bond. There's an asymmetric distribution of charge, with the oxygen showing a partial negative charge, and these hydrogens in the water molecule showing a partial positive charge, right? So that's an asymmetric distribution of charge. And it has some implications here. If you think about that. That asymmetric distribution of charge, by virtue of the amount of electron displacement between the oxygen and the hydrogen, has a magnitude, right? It also has a direction, right? So there's a directional, because of the geometry of the water molecule, there's a directional separation of charge, right? It's not radially distributed, right? It's distributed along a particular spatial dimension, right? So what's something that you know about that has both magnitude and direction? If you guys remember this. It's a mathematical object known as a vector, right? And in the case of molecular structure, or essentially molecular physics, a charge separation like this that has direction and magnitude is known, of course, as a dipole. And dipole, or dipoles in molecules, biological molecules, are super important. Now, there's an additional wrinkle here. You're thinking about water, and this is true of lots of other molecules as well. If you look at those two bonding vectors, those two bond dipoles, if you remember some of your basic linear algebra, they're not just, the overall distribution of charge in the molecule is not going to look like that. Those two vectors are going to add to one another. If you remember your basic linear algebra, what that's going to result in is an overall vector that's oriented in the molecular reference frame that looks something like this, with a partial positive charge here and a partial negative charge here, right? So water is an example of a molecule with a permanent molecular dipole, right? And it's a pretty significant one, right? So if you think back to my example that I mentioned before, about that, the charge-charge separation between a carboxylate group, for example, and a protonated primary amine, right? We talked about that, those dipolar interactions. You guys remember that I mentioned that this is essentially like a couple of point charges interacting with each other, right? So if you think about the electrostatic sort of field lines, you would have that describe the electric field of interaction between these two groups. They're basically radially symmetric, right? Doesn't matter where you put the carboxylate group to a first approximation. If they approximate a point charge to the amino group, the strength of that interaction is going to be the same as long as the radius is the same, no matter where you position them, right? That's not true for molecular, for dipoles, right? So an important distinction for a dipole is the orientation, the strength of the interaction between two dipoles is a strong function of orientation, right? For example, if you have two dipoles and they're lined up with each other this way, what do you think is going to happen? Right? The positive arrow, and people write this shorthand using vector notation for dipoles. The positive always points to the positive end of the dipole. Well, if they're lined up like that, you're going to be in a situation of maximum repulsion for the two dipoles, right? Okay. What about if you had them lined up like this? Well, it can make some sense, right? They're going to be at sort of maximally attractive at that point. Okay, here's a wrinkle for you. What happens if I take my two dipoles and I do this with them? I arrange them orthogonally in space. What do you think happens to the interaction then? Turns out there's no interaction at all. That's the point of zero interaction. They're neither attractive nor repulsive when they're orthogonal to each other. Okay, so that's one of those interesting wrinkles. There's a spatial dependence on the strength of the interaction between two dipoles. Now, I said water's dipole is pretty significant, right? Dipoles typically, people write them down, the scalar magnitude of a dipole, well, either your vector notation or scalar, they usually get the symbol mu, mu sub d. We already used mu once for chemical potential. We're going to use it again for others. It's like the favorite Greek symbol for people like writing stuff down. But mu sub d is usually written out, not written in vector notation, means the scalar magnitude of a dipole. And it can be written down pretty simply. The scalar magnitude can be written down pretty simply. It's simply z times d, where z in this case is the magnitude of the charge separation. Right? And d is just the distance between, how far they're separated from each other, right? Down that sort of, vector distance, whatever. Now, in the case of water, water's dipole, right, is fairly significant, right? As a reference point, sort of a separation of 1 unit, 1 electron unit of charge, separated by a distance of 1 angstrom, right? That dipole scalar magnitude is around 4.8 dBi. That's the unit of measure of the strength of a dipole. Water's dipole, right, is about 1.9 dBi, right? So it's really pretty strong. Okay, now imagine I have salt bridge interaction, charge-charge interaction, like my amino group and my carboxylate group. In vacuum, maximally attractive, really strong. And now I take those guys and I dunk them in water. What's going to happen? Remember, we've got a water molecule with this permanent molecular dipole. What's going to happen to those molecules when they interact with and feel the electric field between those two salt bridge or those two charged ions? What do you think their dipole is going to do? It's just going to sit there, like ignore it? No, it's going to align with that dipole, right? So what's going to end up happening, right, is that the water molecules will align in this electric field. Their molecular dipoles will align in that field, right? And what that's going to mean is that if you think about the interaction, if you were sensing the electric field strength from, say, this point to this point, in the absence of the water molecules, you're going to feel the sort of maximum electric field, maximum sort of energetic tug. But now you put those small molecules down there, those dipoles down in there, the water molecules, they align their dipoles with the electric field. They're basically going to, within the magnitude of that 1.9 dBi, they're going to soak up some of the strength of that electric field. They're going to cancel it, right? And you line up a whole bunch of them, they're all going to do the same thing. They're going to contribute to a partial cancellation of the strength of that field, which is the reason water has such a strong dielectric, because of that permanent molecular dipole, right? And its therefore ability to screen electrostatic interactions is pretty significant. Okay, so that's an example of a molecule with a permanent dipole and the consequences for how it interacts with itself and with other static electrostatic fields. But there are other examples of other kinds of dipoles. All right, and these can come in a variety of different types, right? It's the same basic idea, but how they get formed is kind of different, right? So we talked about a molecule like water that has a permanent molecular dipole. It turns out that you can have molecules that have no intrinsic charge, no permanent separation of charge, and they have no fixed or static molecular dipole, but they can form dipoles. And there's a variety of ways in which this can happen. All right. So if you just as a quick summary here in this little table I'm going to show you, we've got an example of that static interaction between two fixed charges, that electrostatic interaction. And one thing I want you to notice here is the strength of the distance dependence of the strength of that interaction, right? Notice it's sort of 1 over R for an electrostatic interaction. Okay, and we just talked about, say, a dipole interacting with a permanent charge, right? That water molecule interacting with that ammonium group, for example, that protonated ammonium group, right? It's a pretty strong interaction. And look at the distance dependence. It's not as strong as the sort of fixed charge interaction, because dipoles are never generally going to be as strong as a fixed point charge, but it only rolls off as sort of 1 over R squared. So that's still a pretty strong interaction. Okay. Now, how about dipole-dipole interactions? We talked about the orientation, that matters a lot, but it's sort of the point of sort of maximum interaction, or however you orient them, so you have either a repulsive or attractive interaction. And again, this example is a couple of water molecules. The distance roll-off is, now it's gone up, again, 1 over R cubed. So all these interactions, as you get separation between the interacting groups, start rolling off non-linearly, right? And that dipole-dipole interaction drops off significantly faster, and therefore becomes less important, or it becomes irrelevant as a function of distance, much faster than, say, a permanent charge interaction. Okay, now it turns out that there are molecules, like I said, that have no fixed separation charge. They're not ions, and they don't have a fixed molecular dipole. But the nature of their electronic structure lets their electrons move around in such a way that you can create a dipole in them. You can do something that's referred to as inducing a dipole. And a good example of this is the electrons, those delocalized electrons, the aromatic electrons in, say, a benzene ring, right? Those delocalized electrons carry no fixed charge, and there is no fixed molecular dipole in a benzene ring. But those electrons are, by the nature of the pi orbital structure they have, are extremely polarizable. They can be yanked around quite a bit. So if you bring a permanent charge, like a positive charge or an amino group, close enough to it, you can pull the electron cloud, you can distort it, and therefore create a dipole within, or in this case, because of the way it's oriented, across that benzene ring, right? But again, notice what happens to the distance dependence. To get the charge-induced dipole interaction now drops as 1 over R to the 4th, right? So getting weaker and weaker and weaker. You think about the distance dependence. Dipoles can do something similar. Fixed molecular dipoles can do the same thing. You get them up close to a polarizable group, they can induce a dipole, and you can get an attractive interaction. But again, now we've dropped another exponent, right? So the distance dependence of the permanent dipole induced dipole is now 1 over R to the 5th, right? And then there's one other dipolar interaction that's a little funky, right? And this is a situation where you can have non-fixed dipoles induce dipoles in nearby molecules, right? These are sometimes known as dispersion forces. And that seems a little weird, right? I mean, if it's not there to begin with, how does it create the thing it interacts with? It seems like a chicken or the egg kind of problem, right? So to give you a sort of an illustration of that, imagine a couple of molecules, or this could be atoms or molecules, right? It's easier to think about it as molecules that have their associated molecular clouds, associated electron clouds, and they're all their molecular bonding orbitals. And we know from our basic chemistry that the electrons don't just sit there, right? It's a quantum mechanical effect of these electrons moving about, shifting, flitting about the restraint, the structure of these molecules, right? So they don't stay in one position. So they're transient shifts happening on a very, very fast time scale, femtosecond or faster time scales, where the electron cloud around any given atom is not going to be perfectly symmetric. Now imagine we get a couple of these guys and we get them near each other. And that transient fluctuation in one molecule, right, ends up having an impact on the neighboring molecule, right? The transient fluctuations here, we get a little asymmetric separation charge, that's going to tug on the neighboring guy. It's going to kind of do the same thing. And the secret to thinking about these molecules is to recognize that's like a harmonic registration. You get these molecules, you know, off doing it separated from each other, far enough away from each other, nothing's going to happen. But you get them close, they start to feel each other. And then they start to get in sort of rhythm with each other, and you get a harmonic registration of these sort of like, you know, transient fluctuations of electronic structure. That results in a fairly powerful, if there are enough of them around, attractive interaction, right? And this is a classic van der Waals plot, right? That attractive interaction where the London dispersion forces of these electron cloud fluctuations reach an optimum is a really relatively close distance. I don't know if you saw on the previous slide, but that interaction drops off as 1 over r to the 6th, right? So it's really pretty weak. You get too far away and they become irrelevant. It's nonlinear very quickly, right? But once you get close, and close sort of means right up a little bit before and right up to the point that the electron clouds of those, the atoms in those molecules begin to touch each other, get right up near each other. You get this point where that registration becomes quite significant, and you get this quite significant attractive energy that makes those molecules kind of want to stay near each other as they go through their little symphonic, harmonic rhythms of electron cloud fluctuation. Now, as you remember, you can't cram them any closer because the electron clouds of different atoms don't want to be in the same space at the same time. So there's a very, very powerful nonlinear repulsion between these two atoms when they start to get too close to each other, right? So as you bring those electron clouds into contact, they're going to push each other apart. Okay. So as I mentioned, the dependence of that, those London dispersion forces or induced dipole interactions falls off as 1 over r to the 6th, right? So they're relatively weak. There's one more sort of so-called weak interaction that we need to talk about. And this one is a little schizophrenic. It has both electrostatic character and it has some covalent character. And this is an interaction you hopefully remember that is known as the hydrogen bond. Now, hydrogen bonds are always going to involve 2 electronegative elements, one as a donor and one as an acceptor. The donor atom will have a hydrogen atom covalently bonded in that classical covalent bonding interaction. And the donor atom in a hydrogen bond is also going to be weakly acidic. The acceptor atom is also going to be electronegative. It needs to have a free pair of valence electrons that are not involved in another bonding interaction. And it also needs to be weakly basic, right? And so what's going to happen here is that in the donor atom, that, again, like we just talked about with water, the electronegativity difference between the donor atom and its covalently bonded hydrogen is significant, so significant that there's a separation of charge between the two. So this bond has partial, is going to have a dipolar character as a result of the electron withdrawing capacity of that acceptor, the donor atom. In the case of the acceptor atom, this molecule, by virtue of having unpaired electrons in its valence shell, or paired electrons in its valence shell, has got extra negative charge relative to its overall atomic structure. And so it's going to carry a partial negative charge. And that leads to a Coulombic charge type interaction. But in the case of a hydrogen bond, that's where this acidity and basicity issue come into play. In a hydrogen bond, it goes beyond just that dipolar interaction. What happens is when this hydrogen bond gets close enough, and that distance that is close enough is somewhere in the range of typically 2 to 3.5 angstroms, right? When that happens, and if those molecular if the orbitals of the unpaired electrons on the donor can line up effectively with an appropriate nascent molecular orbital on the hydrogen, you can get a partial sharing of the hydrogen atom as it basically interacts with the electrons from the acceptor, but doesn't break its bond with the donor. So the hydrogen bond shares partial covalent character as a result of this bonding interaction, but it requires two things. It requires that the donor and acceptor be close to each other. It also requires that they be lined up, right? So the orbitals that participate in this hydrogen bond have to be oriented with each other to pick up that partial covalent character, right? Now, the atoms that we're going to need to worry about that are going to participate in hydrogen bonds like this, they're really only a couple, the vast majority of things we would worry about. And mostly it's going to be oxygen and nitrogen, right? So you can have a good hydrogen bonding example would be, say, an alcohol group acting as a donor, contributing a hydrogen to a carbonyl oxygen, or to an ether oxygen, or to a tertiary amine group, right? Another good donor interaction would be like a primary amine, right, with its associated hydrogen bond, or even a secondary amine, that then acts as a donor with its hydrogen bond shared with a carboxyl oxygen or an ether or a tertiary amine. Okay, so real quick, how weak is weak? I keep calling these weak interactions. How weak are they? Just as a reference. All right, so covalent interactions, right? Those are pretty daggum strong. You know, many hundreds of kilojoules per mole. Which is one of the reasons, you know, molecular structure is as stable as it is because once you get these stable covalent bonds formed, man, they're really good, right? That electrostatic interaction I mentioned, that sort of charge-charge salt bridging interaction, you can see how that drops off pretty dramatically compared to a covalent bond. And this, I believe, is the vacuum energy of an electrostatic interaction, but I'm not 100% sure of that, but I think it is. And then you can see that a hydrogen bond is about, 4 times less strong than, say, an electrostatic interaction under the same set of conditions. And then we come on down here to these dipole, say a fixed dipole interaction, and we're down about another order of magnitude, right, between, say, an electrostatic interaction and a dipole interaction. And we come on down here to these London dispersion forces, and we're down at least another order of magnitude, if not just a 30-fold or something like that. But what these guys down here lack in intrinsic strength, they can make up in numbers, right? So you can have huge numbers of these that, without understanding some of the basics of how they work, you can't understand molecular structure because they're critical to putting important molecular structures together. Okay,